Erwin Huizenga, who will take us through the topic from research to ready with Google.
Erwin is a staff developer relations engineer on the Developer Advocacy team at Google. In this role, he focuses on machine learning operations and large-scale machine learning. Previously, Erwin was responsible for leading Google's ML practices in Europe, Middle East, Africa, and the Asia-Pacific regions. In this role, he has worked with customers like Spotify, HSBC, Gojek, Sharechat, LG, and Woolworths. Erwin has a decade of experience in the field of machine learning, data science, and cloud computing. Erwin, we warmly welcome you to our AI forum, and thank you for joining with us today. The stage is yours.
Yes, thank you for unmuting me. Hi, everyone. Thank you for having me. I hope everyone can see the slide. So today I'll be talking about how to go sort of from research to ready and solving for the future in the context of artificial intelligence, the topic of today's event. And I want to talk through some of the groundbreaking research we've done at Google and how this fuels a lot of our products and how this is fueling a lot of the innovation that is happening these days. I want to highlight a few key areas around natural language processing, model generations, image processing, all topics also related to things like metaverse and Web3. So already there was a short introduction of myself, but let me do it a short one again. So my name is Erwin. I am based out of Singapore, and where I work as part of the machine learning team, focusing on things like machine learning operations and large-scale machine learning. And also I'm a startup advisor, so I work with a lot of startups across Asia and advise them on their journey fueling innovation as well. Feel free to always add me on Twitter or LinkedIn if you want to have a chat about some of the topics that I'm discussing today. So there's a lot of things that I want to discuss today, so I'm suggesting that we dive into it right away. In the end of the talk, I'll also leave some time for Q&A. So if there's any questions that you have during my talk, feel free to ask them as well, and I can take some of the questions in the end as well, and we'll leave some time for Q&A as well. Okay, so research at Google. So you probably heard a lot about Google and research and how we think about research. Research is essential for us as a company. It's essential for our innovation. It has been in the past, but also it's essential for all of our innovations in the future. And the philosophy that we have across Google research is that we strive to create an environment conducive to many different types of research across many different timescales and levels of risk. So when doing research as a company, there's different timescales that we have. Some of this research is more short-term focused, others are more long-term. And also there's different levels of risk, of course, when doing research. Some things we're pretty sure that work, other things are more like a moonshot, where we're not sure where we're going to end, but still we believe that it can be groundbreaking and it can take us in directions that we maybe haven't thought of. And at Google, research is very important also because it drives a lot of the products and the technology that we have and that we use for on our platforms. So a lot of our products are powered by our research. So this goes from, of course, Google Search that we all are familiar with, to things like Google Maps, of course, but also more newer projects like Google Waymo, AlphaGo that you have maybe seen on Netflix, the documentary, but also, of course, Google Cloud. So a lot of this research sort of ends up in our products and fuels our products. And I think that's very important when we look at research and how it drives innovation, is that it's important to think about, so how can we take successful research, or how can we take research and embed it in our products and improve the experience that our customers, our users have overall. That's very important for us at Google. And how we tend to do this is, of course, our research teams work and collaborate very closely with our product team. So from Google Search all the way to Google Cloud. So research teams try to align and work with these product teams. But there's two different paths that you can follow, right? When you want to process through this research, is that first of all, it can end up in a product. So research can end up in a Google Cloud product, for example. So one paper we published is about Dremel, and Dremel has become Google BigQuery on Google Cloud. So this research then not only becomes available for internal Google teams, but it becomes available for the wider customers that Google Cloud works with. But also another path that we follow is the one in green in the top, is that where we take research and we open source it. And that was already during the opening talk, we heard about the importance of open source, and also in the metaverse context, is that I really believe that open source enables developers, enables organizations to also innovate and progress. So a lot of this research then also can end up maybe in the open source space. And some examples of this is things like Hadoop, but also a very famous one, a very popular one as well is TensorFlow, a machine learning library, a machine learning framework for building machine learning models, and also more recent open source work around Kubeflow and building these machine learning platforms at scale. So there's these different routes how things can drive innovation and how things can drive a product pipeline. I think this is always very important when you come from this research angle to think about how can we drive actual impact through open source or through landing this in products as well. And how this relates and why this is important. So AI, I believe, is going to be a very important enabler for innovation in the future, and in the short-term future, also for the long-term future. But also it's going to be an enabler for the metaverse as well, as has been mentioned in the opening talk as well. Is that research and AI have been impacting the merging of virtual, augmented, and physical reality, and blurs the line between interactions in online and in real life. So AI is a very key enabler in this. And I want to talk about some of the core technologies, research, and actually products and tech that can help drive this innovation across the board. When it comes to use cases, I believe there's a lot of different use cases. And I think I always believe in thinking in the art of the possible, right? So there's use cases around natural language understanding. So how do we take language from a human? How do we understand and take action on that? We see a lot of development on large language models. I especially see this across the region where Sharechat is also present, so in Asia, but also we see a lot of innovation on generative adversarial networks, so generating things like text or images, which is of course very important for the metaverse as well. And there's a lot of research around the image models in general. So from a research perspective, from a use case perspective, you see that this research is heading in all of these directions. And I talked about the art is possible, right? And if I showed you this painting, you'll probably think about this painting that this is something that a human has worked on for a very long time and gone through the creative process of creating this painting. But actually the mind-blowing thing about this is that this is not an actual painting. This is a painting that has been generated by an AI model. This is the Théâtre de l'Opéra Spatial from Jason Allen. And it was submitted actually to a art contest, and it won the art contest. So it's a text-to-image diffusion model, so a model that takes text and generates an image, a painting in this case. It took 80 hours of work. There's a lot of images that were generated and used for training, and there's a lot of cutting-edge models that have been used to do this. If you would have asked me 10, 15 years ago, can an AI model generate a human-like painting, I would have probably been in doubt and not sure if that was possible. Now we see that this is even possible nowadays. So a lot of this groundbreaking research and AI is happening these days. But there's more than only with GANs generating these image art type of models. I want to talk about two topics today that I think are groundbreaking as well and can impact a lot of the innovation that's happening, if it's innovation within the telecom space or a metaverse or even, of course, things like Web3. I think this is a lot of groundbreaking things, and we see a lot of organizations looking and moving into these directions. And I want to talk about some of this research and how this led to actual products and actual use cases being implemented. So the first one I want to talk about is vector search. So vector search is important when you take an input from a human, could be a text input, and then you maybe want to use that input to search in a database of articles or in a database of news. And you want to search those articles based on the text query. So you could do this by doing just keyword matching. So take the input and try to match that to see if that keyword or that input matches to something in your, so to the articles in your database, to say so. But this is very slow and this is very basic technique. So what you actually want to do is you want to do something like semantic search. So this is the idea of taking a piece of text and finding another text that is sort of similar to it. Not exactly the same, but very, very similar. So not only because it contains the same words, but it's semantically similar. So to a human being, these two snippets of text are very, very similar. This basically is, by the way, the problem that Google search tries to solve, but also that YouTube tries to solve. When you enter a text query in Google search, which web page is the best match for you as a user? Or when do you search for a YouTube video, which one is most relevant for you? For many, many years, this problem was ridiculously difficult to solve. It's very difficult for computers to solve. For us humans, it's natural, right? But in the past decades, it's become solvable thanks to techniques like vector embeddings. So where we try to represent something like a text or an image as a vector, so as a numeric representation. Actually, one of the first groups that done some amazing research on this, with some very well-known Googlers like Jeff Dean and Greg Corrado, was on efficient estimation of word representations in a vector space. So this research was already done in 2013, so almost 10 years ago. And it introduces a way, it's called word2vec, which is a very famous paper, and a way to embed individual words as a vector. And how it looks like is what we try to do is we take these words and we put them in a multi-dimensional space. So if you build natural language processing models, you're probably familiar with word2vec. And here's what it looks like. So we map this, like I said, we map these words into a multidimensional space so that the words that are semantically similar, so not exactly similar, but semantically similar are clustered together in groups. So I'll give you an example. For example, computer and programmer, or computer and robot. So we know that these words are semantically similar. And this technology drives a lot of the natural language processing applications that we saw, right? For example, in the case of customer, interacting with customers, understanding their questions and trying to give them an answer. But nowadays we can even do better, right? So yes, word2vec is still used, but there's techniques that are better. So research has progressed over time. This is actually a paper that has been published in 2008 by Google as well, where we can embed entire sentences or paragraphs, essays, into an individual vector. So we're not embedding a word, we're embedding maybe a paper like this, or we're embedding a full piece of text that a customer has wrote. This comes from Google research as well, from, like I said, in 2018, and it has made it a lot easier to do applications like text search. So how do we know an article is similar? So we want to create these embeddings and see how articles or how results are similar to each other. And then we want to put them in that embedding space as well. So often this research is published, and what we try to do, as I mentioned, is we follow these different routes of making this research applied and making it available to the community. And one way we do this is through our TensorFlow libraries, and TensorFlow Hub is is part of the TensorFlow ecosystem. So this research, this universal sentence encoder, has been made available on TensorFlow Hub, so has been open source for folks to reuse. So we see a lot of organizations, a lot of teams reusing this research for their own use cases, applying it for their own use cases. So the way that we do this for text similarity search is with text embeddings, right? Nowadays, there are also embeddings for all sorts of data types, right? And a good example is image embeddings. Allows you to do sort of reverse search with images. So for example, in this case, if you've seen a shoe and you want to find a similar shoe, you can do image search. And the cool thing is we can now nowadays embed not only images or text, but we can also combine these embeddings, so combine these vectors. So let's say we can take an image, combine it with the customer information, so that we know about the customer, and use those different embeddings to even improve the search for, in this case, if it's image search. So we're using other data types as well and other type of embeddings and combine them to provide better results as well. So we can embed different types of data, and with sort of the multimodal vector applications, as we like to call them, and we like to match that with the user. So the applications that we're seeing using these type of vector representations, these type of embeddings, is the use cases are, there's a lot. That's just it depends on how creative you can be, and you can apply them in many different scenarios as well. So, and where we see a lot of important research, and what I think, in my opinion, is very cutting edge at this moment in AI, is what we call neural deep retrieval. And the process of neural deep retrieval works like this. Everything, of course, starts with data again, and data could be text, could be images, could be more structured data. And then we generate our embeddings, our vector representations through deep learning models. So probably all of you are familiar with deep learning models. They've been around for a long time, and they now are applied to many, many different use cases. But they generate these embedding representations where we take this data and put it in a multi-dimensional space and see if we can cluster them together. So embeddings are vectors that are similar. So images that maybe are similar, or text that is semantically similar. And then there's a two-step process. So first of all, there's similarity matching. So typically what we do is that when the problem that we have is that if me or you as a user are doing a search, or you're using an image, do an image search, is that we have to take that input from you and then have to map that to the enormous database that we have, or all the data that we have. And doing that is very, very challenging. So we have to find this, we have to do, first of all, similarity matching. So we have to take your input and match it to similar items. So let's say if you're searching for an article or for an answer on your question, you have a question about your phone, the Pixel phone was mentioned, you go to the website of the telecom provider, and you have a question about the phone. And then taking that question and finding the right answer, or answers that are close to your input, is very challenging. And then once you have a group of those options, you want to rank them, right? You then want to apply something like ranking or scoring to rank those options and provide the best option to the user, the actual prediction. So it's a multi-step process. Again, to sum it up, you generate the embeddings, and given those embeddings, you have to retrieve the best options, giving the input, and then you have to rank those options. Neural deep retrieval. Doing that is complex already if you do it on a smart scale and on a smaller scale. Let's say you have this running on your laptop or in a notebook if you're a data scientist. That is already challenging to get working. But operating these systems at scale, and maybe at the scale that Axiata has, is something that is more complex, right? Because you have a lot of customers, you have a lot of users, you have a lot of data. So things become more and more complex. So given a query, a vector, so it could be a text search, how do we find its nearest neighbors as quickly and as efficiently as possible? Quickly meaning with low latency, efficiently as possible, is that we don't want to have a lot of compute running all the time and pay a lot of money to run these queries. So we have to balance accuracy, latency, and efficiency. And that is not easy to do, and that is especially not easy to do at scale. So in a research setting, things are nice, but now we're hitting the challenge like, oh, where are we, how and are we going to run these use cases in production? This is where vector similarity search comes in, also known as k-nearest neighbors or approximate nearest neighbors. So giving a input, a vector, we want to find its closest or its nearest neighbors. So if we have an image of a shoe or we have a search query, what are the closest results to that? So, and because then we can take those results and rank them and show them to the user. This is a critical step in most neural deep retrieval architectures. And this is not an easy thing to do because you have all these options and how you're going to find the best results in a short period of time. This is where again, the research to product comes into play, right? What we've done with this research that that Google has done, we've embedded that into a product that is used by Google teams internally and is even available on Google Cloud for folks to use. So it's a massively scalable vector similarity search capabilities. So the thing is that I talked about is that what we want to do is we want to find with low latency the nearest neighbors just in a few milliseconds, right? Because most of these applications that we have nowadays, users and customers are used to the things happen quickly with very low latency. In the metaverse, it will be the same. Things have to be fluent. Things have to be quickly. Of course, this needs to be highly scalable, right? So if the users grow, the number of users, if the number of search queries, or if the number of image search or grow over time, we have to be able to scale these applications as well. And of course, we want to do things cost effectively as well, right? So this is where we developed technology, we researched, we made it available on Google Cloud as well as a matching service. So, and what we actually do here is leverage Google Cloud, Google research technology that we use internally for our services as well and make it available. So we try. So there's been this research on from 2020, which made significant headway in solving this problem. And what we've done is we designed a new algorithm, which is called SCAN, S-C-A-N-N. So scalable approximate nearest neighbor search. So again, we're trying to speed up the calculation of the distance between vectors and do that at scale. So we have to approximate. So let me explain what that means. Is that if we, for example, do an image search, so you take the image of the shoe and you want to find similar shoes, is that we can't search through all of these shoe images that we have. So what we have to do is we have to calculate the distance. So the image that you use to search, we have to calculate the distance with all the images that we have in our database, because we want to have the distance that is the closest, right? So the images that are most similar to the one that we're using for the search. And so we have to calculate what we call the distance between those vectors. So you remember the word cloud that I showed earlier. So we will want to find the words that are closest to the one that's our impact. And we can't do that for everything. So the way we try to do that is through approximation. And one of the most popular techniques to do this is with quantization. So we take these millions of options, millions of vectors, and we actually map them to a smaller set of points so that we can approximate the distribution of the entire set. So it's all about this approximation as well. What this research paper published in 2020 is that we introduced this, as I called it, SCAN algorithm. So the SCAN algorithm found a better way of mapping. So taking this used data set of vector points and map it into a smaller one. a technique that we call anisotropic vector quantization. What it allows it to do is find more accurate the nearest neighbor for a data point. And it also, remember, low latency is important, allows us to do higher queries per second. So we can do more queries in a second. So we built this internal engine, and it powers things like Google Search, YouTube, but also a product on Google Cloud, Google Matching Engine. So what this technology can help us with is improve use cases like recommendations, like search, and we can improve through this cutting-edge technology the customer experience that people are having on the platform, or even in the future on the metaverse. Another area of research that we are very, very excited about, and that is impacting a lot of the innovation that we're seeing across the board, is neural architecture search. So the challenge that we have when we go from research to having something in production, to having an ROI or having a return on that research investment, is that the challenge there is that iterating fast through the process, especially when it comes to AI. So how we did this in the past is that we had a research. So if we all think about our research days, or when we were in university, or when we were in college, is that we have to collect data, we have to think about the best approach, we have to develop it, we have to test it, so on and so forth, which is a time-consuming process. So how can we speed up this process, and how can we especially speed up the design of new AI architectures? So given a use case, could be any use case, what is sort of the current best architecture to apply to that use case, which is in the past was a very time-consuming, human-intensive process. This is where neural architecture search comes in. So what it is with neural architecture search, or NAS, is a technique for automating design of neural networks. So this is a AI model designing the architecture, AI architecture for a given use case. So in a typical NAS setup, there's a controller that proposes machine learning models, so sampled from a search space. So this controller generates model architectures. And then these architectures, what it does is they are applied to the use case. So if you do recommendations, if you do image classification, it will then apply these architectures to the use case. It will train it, and it will measure its performance, and it will iterate through the process. So generating new architectures until it finds a given architecture for a problem. This is how now a lot of these state-of-the-art models are designed. How did this all? So what it does? It's the controller gives us the ability to speed up the process of designing these architectures, and we can balance even things like accuracy and latency. Right? If we need to do predictions at the edge, we need to do this with a smaller model, but still with high accuracy but low latency. We can design these type of architectures in an automated way. So how does this all start? And I'll take a quick sip of water. So in 2016, Google researchers published a paper called Neural Architecture Search with Reinforcement Learning. I think there's a talk on reinforcement learning as well during these 2 days, if I'm not wrong. In this paper, they showed the researchers how a recurrent neural network, which is a specific type of neural network, can generate model descriptions of neural networks. They trained this RNN, so recurrent neural network, with reinforcement learning to maximize the expected accuracy of the generated architectures on a validated set that we have. Using this method, they were able to design novel architectures on the data set, which is the CIFAR 10 data set, which is a famous data set. And these architectures are designed based on expected accuracy of the model. So since the paper, the research field has continued and speed up even more, and including reinforcement learning based techniques. There are also now there has been introduced PyGlove, which is a symbolic language that we can use to help convert your machine learning code into a NAS program. So you can generate machine learning code and it then becomes a NAS program that designs these architectures for you. And the cool thing is that, again, this research has been adopted across Google, but not only across Google, but also by other Alphabet teams. Waymo, the self-driving car arm of Alphabet, has been applying this technology in one of those use cases. And I think the fun thing about this is that when we have these, when we have AI, neural architecture search, NAS, designing these new type of models and new type of machine learning, is what we see is that they come up with very interesting new architectures that maybe we as humans have could never design. So they actually mix layers in the neural networks that we maybe haven't thought of, or skipping layers where we didn't think of it. So the designs are very, very interesting for look at. So very creative combination as well of layers. And we've seen is that this has helped us innovate and improve our use cases as well, in this case for autonomous driving. But also we see this used across Google and with other teams as well. So for example, the Google Pixel 6, and we wanted to do efficient energy phase detection. So through NAS, the team was able to generate a model with the same accuracy, but a model that uses 70% less energy. So it's not only about accuracy. We talked about latency and efficiency. And energy efficiency is something that's very important for us at Google as well. We heard in the opening talk as well. So through using this technology, through using this research, the team was able to come up with a more efficient model, but not compromising on accuracy either. And here again is that what the team has done is that they have not only done the research, they have not only embedded the research within the Google products, but also this technology is now available for developers, for customers to use as well, so that other industries can benefit from this technology as well. Through, in this case, for example, the Vertex AI platform, where we have a neural architecture search API and service. So it can help the team with building models faster, designing new architectures, improving existing models in a flexible and scalable way as well. We believe in enabling other organizations through our research as well. So what powers this progress, right? And I want to stop here for a second to think about this, is that the progress in the past 10, 20, 30 years, 50 years, it has been immense, right? And I feel that it's even speeding up more and more and more. If we look at the AI space, the number of research that has been published is growing every year, and it's even more impressive every year. But applying that research to actual use cases that we talked about, and applying that research to innovation in the future, like that we talk about today, like metaverse or Web3, is something that is challenging, and that but we've gotten better and better and better at. And why have we gotten better? It's, of course, the research has gotten better, the technology has gotten better. I've talked about all of that, right? It's technology is now available on the cloud platform, Google Cloud. I talked about some of that technology, so that the enablement is there. But there's also two other things that we all often talk about as well, and that are still important, is that the size of the data is still growing. The quality of the data is improving over time, and we're getting better at using not only structured but also unstructured data, as we talked about that as well. And so all of that enables also that we get better at applying this research in production type of settings. It also adds a lot of complexity that we talked about. So how do we do this at scale? How do we do this efficiently? How do we do this with low latency? All of these things become more and more complex when the data grows as well, right? The quality of the models improve, but also the complexity increases as well. But also what we've seen, and where we've seen a lot of innovation, and especially we've seen this, we talked about this a lot at Google, is that the computing power has helped, has become so much more efficient, and we have now things like TensorFlow processing units, TPUs, and you see generation V4 here on the slide. These are what we call our TPU pods. So these are like a supercomputer, and this is used only by research teams to train these models at scale, but also we see this used by organizations and companies to train models for their use cases. And what we, for example, see a lot is happening applied research, or actually applied use cases around large language models. So through the growth of data, through our improvement or innovation when it comes to computing power, we've been able to get better at applying research in production as well. And especially this work that has been happening on TensorFlow, on TPU, so TensorFlow processing units have been, tensor processing unit has been immense and mind-boggling for me even. And it will only, like I said, speed up and continue. So there's so much exciting stuff happening as well. And a lot of this research and technology innovation is, I think, driving a lot of the change that we see in the future. So I just want to do a short recap of what we talked about. So yes, I fully agree with what has been said in the opening talk as well, but that AI is a very important enabler for innovation, that AI is also an important enabler for things like the metaverse, but also other types of innovations around Web3 we talked about, is that AI will only keep speeding up that innovation. And some of the key areas, and of course there's way more beyond this, but we don't have enough time for that today, is that we see things like around embeddings, a lot of amazing work about similarity search. We see a lot of great work around neural architecture search, so designing new types of neural networks. So there's a lot of exciting things happening, and I hope you've taken or learned one or two things from today's talk. I just want to thank everyone for being here today, and thank you everyone for joining this keynote as well. So I can now, if we have time left, take a few questions. Are there any questions that we have? Okay, there's 3 questions, and I'm looking at my device, my Pixel, because they are shared there. Yes, great first question. So let me first read out the question. Will non-data science people be able to build ML models with new advanced AI and ML cloud tools? Great question. Thank you for asking. Yes. So I feel that is, I haven't talked about that today, but one of the biggest innovations I feel that's happening right now is that we're, through technologies like we talked about today, that are then being used and implemented in solutions, but also things like automated machine learning toolings. So if you look at Google, we have on Google Cloud AutoML, which enables business analysts, folks that are not as technical as data scientists, or even or maybe engineers who want to quickly build a use case. They are enabled through this technology to go through the interface and quickly train and deploy these types of machine learning models. And we see this used a lot in applied as well in use cases. So great question. And yes, I see that there's a lot of innovation happening there as well. And these automated tools, automated machine learning tools, are enabled through that.
For the question number 2 from our audience, Erwin, Can we use neural deep retrieval architecture for high dimension tabular data with auto-encoder vector representation?
As I mentioned, for use cases, combining different types of data. So could be things like images with more structured type of data that's maybe very sparse. So we see a combination of data, and I think that's going to be the future as well, where you combine different types of data. You see that already happening a lot in recommendation systems, right? You have user data, and you have maybe something like a product that you want to recommend, or an image, or a video. But yes.
Okay, we have another question. Is NA part of current GCP AutoML?
Another good question. It's yes, that is also the short answer. So a lot of these technology and research drives a lot of the products that we have on the platform as well. And I think we've always been pretty good at that. Is making sure this research lands in products, for example, on Google Cloud AutoML. So yes, it's part of that as well. But you can also use it as a separate service on Google Cloud as well for your use cases that you have. So there's different options, there's different flavors depending on what type of user you are.
So Erwin, the last question from our audience. What is the applicability of Google Pixel 6 for federated learning?
So I don't think federated learning is tied to a specific device, and I'm not very familiar with all the Pixel hardware. So I would divert that question to look at what we have on the TensorFlow federated learning website, or even on the Pixel specs. But I think there has been some work on specific hardware on phones these days with Pixel, but I'm not part of the Pixel team, so I want to be careful with my answer there. So, but it's again a great question.
All right then. Thank you, Erwin, for enlightening us on the research methods at Google and how it has been applied for Google productization.